in the last previous several of the classes, we have been talking about the synthesis of industrial polymers, and currently we are speaking about synthesis of nylons, and in fact we have gone beyond the synthesis of nylons and we are talking about the structure property relationship of nylons. So, we will start right there. So, we had been talking about the effect of moisture content and the effect of increased temperature on nylons, and we told that both of them moisture content, increased moisture content and increased temperature, both will have the same effect, that is it will increase the segmental motion of the material, it will decrease the stiffness and the tensile strength of the material, but in turn it will increase the impact strength or the toughness of the material. So, you would better use a nylon which actually contains less amount of water in equilibrium when it is exposed to a certain amount of moisture than say a lower nylon. That is because for insulation purposes, for electrical insulation purposes, because for this kind of applications you do not want lot of water to be present, because otherwise the resistivity of that will decrease and insulation will not be effective. So, you go to say for example nylon 11 and not use nylon 6 for electrical insulation. And we also, so in effect then what we talked about, if we have to summarize this particular part, then we could say something like this: higher proportion of amide groups, this leads to higher water absorption, and the effect of higher water content is basically analogous to the effect of increase in temperature. And so, you can say that this moisture basically has a plasticizing effect, because the material becomes less stiff, segmental motion increases, the toughness increases, impact strength increases, plasticizing effect on modulus or the Young's modulus, it goes down. So, as a matter of fact, if you look at say nylon 6 or nylon 6, then the Young's modulus, value, it goes down by as much as 40% when these materials they absorb around 2% moisture. So, just put around 2% of moisture and the Young's modulus goes down by 40%. So, the effect there is basically enormous. Now, in general, if you look at the applications, of nylons, they are typically as fibers, because they are having quite high tensile strength. Typically, the materials are having quite high tensile strength and also stiffness, and I also mentioned how tensile strength and stiffness are two different things, and they are also resistant to attack by different solvents because of this very strong packing, high crystallinity, so on and so forth. And so, up to around 90% of world production of all the nylons can be accounted for by its usage in fibers. So, up to around 90% is used for fibers, and rest of that is used for plastic applications, and typically for because of their high cost, they have not become your general purpose material, like if you compare with polyethylene or polystyrene, like that. Now, because polyethylene, polystyrene, these things are typically available at 1/3 of the price of nylons. So, about plastic applications, nylons have not gained much ground with respect to the other commodity polymers. These nylons are engineering polymers. With respect to commodity polymers, they have not gained much ground because the cost is much higher. However, they are used as fibers. 90% of their production can be accounted for by their use as fibers. Okay. So, because they have very optimum combination of toughness, rigidity and very good heat resistance, quite reasonable I would tell, because the melting points are quite high, say around more than 200 degrees Celsius, so on and so forth. Now, what we will talk about now is something else, but still the topic remains polyamides. So, until now we have been talking about mainly aliphatic polyamides which have the trade name nylon. Now, we will shift our attention to aromatic polyamides. So, aromatic polyamides. Now, aromatic polyamide fibers are generally known as aramid fibers. Now, you will tell they are aramid fibers, and how do you define this term aramid? So, it is defined as a long chain of synthetic polyamide, polyamide in which at least 85% of the amide linkage, they are attached directly, to two aromatic rings. Then you call them as aramid fibers, two aromatic rings. Now, synthesis wise it is quite different from how you approach the synthesis of aliphatic polyamides, because if you are using a diamine and a diacid for the synthesis of the polyamide. So, it is basically an amide formation reaction. Now, in this case you have to then use a diamine which is an aromatic diamine, and you have to use a aromatic diacid. The thing is, the reactivity of aromatic diamine is significantly lower with respect to their aliphatic counterparts, because the lone pair on the nitrogen, you see that the nitrogen lone pair has to attack to the carboxylic acid unit. So, this lone pair of nitrogen is less available because of the resonance stabilization with respect to the aromatic ring. You can displace them into the aromatic ring in drawing different resonance structures. So, they are not as easily available. So, the reactivity of these aromatic amines is lower, and that is why what you do is that in this case, if you used just a diamine and a diacid, an aromatic diamine and aromatic diacid, because of the lower reactivity of the aromatic diamine, you would require significantly higher temperature in order for the reaction to proceed, which is not practical, because at those high temperatures your material might degrade. So, you want to still do at a lower temperature, and that is why what you do is you take the aromatic diamine, you take the aromatic diacid, but you activate the aromatic diacid. So, what you do, instead of using aromatic diacid, you use aromatic diacid chloride. Okay. So, diamine plus diacid, this reaction is not used. So, what you do is that you use a diamine and you use an activated diacid, the derivative of that is diacid chloride. So, an example could be, let us say you react this diamine, this is actually metaphenylene diamine. You react that with this diacid chloride. Now, this is isophthalic acid if you have CO2H on both sides. So, this is isophthaloyl chloride, So, this is already an activated material. So, the electrophilicity of this carbon is increased because of the electron withdrawing effect of chlorine that compensates for the reduced reactivity of the amine, and what you get is liberation of HCl and a polyamide of this kind of structure, NH, CO, okay, CO. This is a polyamide. So, basically this is a I have drawn the structure wrong, because this is in meta position. So, this will be not here. Actually, let us draw the structure in a different way. So, this is not the right structure, because here I have drawn in the para position. This should be the structure here. So, you have NH and then NH, okay, CO, CO. So, this is meta position. Okay. So, this is called a meta aramid. This is a meta aramid, meta aramid. So, this is poly metaphenylene isophthalamide. Okay. So, this is poly metaphenylene isophthalamide, and the trade name of this compound is Nomex. And the polymerization, these polymerizations are typically they are carried out in solution, and the solvent that you are using is a highly polar solvent, but this is aprotic solvent also. Unlike water, water can donate protons. Polar aprotic solvents you are going to use here. Say for example, you have, I mean just an example, DMSO, dimethyl sulfoxide, is a polar aprotic solvent that you are not going to use here, but in general polar aprotic solvents are solvents which are polar, but which do not have the ability to donate protons. So, in this case what you use is dimethyl acetamide. So, this is acetamide, CH3CO NH2. So, instead of 2 hydrogens, if you have 2 CH3 units, it is dimethyl acetamide. This is a polar material, polar solvent, but this cannot donate protons. So, polar aprotic solvent. Temperatures are typically less than 100 degrees Celsius. Compare that with the temperatures that we use for your aliphatic polyamide preparation, upwards of 200 degrees Celsius there, and here because this is activated, you do not need very high temperature, and you typically use a base in order to scavenge the liberated HCl, the acid, and the choice of the solvent is dictated by the fact that the growing polymer chains should not precipitate out before the polymerization has not reached the intended molecular weight. Remember that your temperature here is low, so the solubility of this material might be lower in the solvent. So, if that is the case, then it can prematurely precipitate out before a high molecular weight is reached. In order to stop that situation, you are using a highly polar aprotic solvent in which it has good solubility, and that is why it does not prematurely precipitate out before you have reached a chain which is of long enough length, that means high enough molecular weight. So, because the temperature that you are using here is much lower than the temperatures that you use for your aliphatic polyamide synthesis. Now, this is a meta diamine, you are reacting with a meta diacid chloride. If you start with the para version of this, that means paraphenylene diamine, if you react with, what is that compound? If you have CO2H here and CO2H here, that will be terephthalic acid, that will be then, you will be then reacting this paraamine, which is your paraphenylene diamine, with COCl, COCl, terephthalial chloride. If you react that, and then what you will get is the para version of this material. The para version of this material will be paraamide, that is this NH, CO, this is your paraamide. Okay. Now, this paraamide that you have here, the trade name of this paraamide, so this is a paraamide, trade name of this paraamide is Kevlar. So, already now we have described the synthesis of Nomex and Kevlar. Now, if you compare between Nomex and Kevlar, you see that Kevlar has all this para orientation. So, ultimately the chains they can pack better than your meta aramid. So, and typically the Kevlar is the most well studied material, and when you are making fibers out of this, you will see, since this is para orientation, so this molecule in the extended form, it can orient along the direction, along the long axis of the fiber. All these molecules will orient along the long axis of the fiber, that will give the fibers enormous tensile strength up to 3 gigapascal, approximately, and you will have all these hydrogen bonding interactions in the transverse direction. Okay. So, you will have hydrogen bonding interactions in the transverse direction, and in the longitudinal direction they will just pack nicely, they will be just parallel like that, and also you will have these pi stacking interactions between the aromatic units of the subsequent layers. So, all these things will make the material highly anisotropic, because along the length of the fibers, because they are all oriented along the length of the fibers, you will have enormous tensile strength, and along the transverse direction of the, so this is the length of the fiber. So, along the transverse direction you will have the hydrogen bonding interactions, which is definitely weaker, because along this length you have the polymer chain itself, which has covalent bond between the molecular units, the covalently bonded compound, the chain is extended along this length. So, the tensile strength is quite high, but if you see the transverse direction, which is this direction, in this direction you will have hydrogen bonding interactions, and so that is weaker. So, that is why you will have the properties that will be enhanced, your mechanical properties will be enhanced along the length of the chain, and they will not be that much enhanced along the transverse direction. That is why it will be an anisotropic, it will have highly anisotropic property. Your para aramid fibers or Kevlar, it will have highly anisotropic property. Now, something also you should remember, these are all rod like molecules, these are all rod like molecules, and this kind of efficient packing of these molecules not only make them very highly crystalline, but also it makes it difficult to solubilize in many different solvents. So, the processability is also, you have to adopt different ways for processability. So, normal drawing of the fibers may not work. What you have to do is you have to use something called a spinning techniques. We will come to this. You have to use spinning techniques, say in this case it is solution spinning technique or weight spinning technique. In fact, this is weight spinning technique or weight spinning process that you are going to use in order to process these materials into fibers. Now, and of course, these aramid, these para aramid fibers that you are going to produce, they are used as cable or rope products, so on and so forth, and the production is expensive because the processing is also expensive. So, we will come to that now. So, typically what you do for processing of these aramid fibers, because we are not going to talk about meta aramid fibers anymore, we are going to talk about para aramid fibers. So, before you come to processing, you should also have another look at this particular reaction by itself. If you compare these two reactions, this reaction is done in dimethyl acetamide, temperature is somewhat less than 100 degree, and if you are talking about the preparation of the para aramid, which is Kevlar, then typically for this preparation what you do is, these are your starting materials and the solvent that you are using is a mixture of hexamethyl phosphoramide. So, this is your hexamethyl phosphoramide you are using, and along with that you are using N-methyl pyrrolidone, which is this molecule, N-methyl pyrrolidone, and you are taking that in 2:1. So, this is 2, this is 1, 2:1 ratio, the temperature is minus 10 degrees Celsius. So, you do at quite a low temperature this particular reaction. Now, let us come to the processing of this material. So, what you typically do, as I already told you, that this is a weight spinning technique. We will come to what a spinning technique is slowly. So, the point here is that you start with a solution of the material, you start with a solution of the material with a specific properties, and you see that you have to have fibers that have come out ultimately after processing. Those fibers are in the solid state and they have a long range, strong orientation along the length of the fibers, that is what you have to achieve. So, what you start with is a highly concentrated solution of this para-aramid that you have prepared. So, because so ultimately what you will get after the reaction, you will get pellets of this material and then you pulverize this material and then you dissolve in a suitable solvent. I will come to what solvent you are going to use for para-aramids, but let us look at the properties that you would like to have in this precursor solution. So, you start with this solution and the idea is you will force it through something which is called a spinneret. These spinnerets, if you look at the script here, these spinnerets are nothing but they look like the shower heads. So, these shower heads will have lot of holes in it. So, what you do is push your polymer solution through this, you put lot of pressure and you push it through this, and that way you are actually orienting the material, the first thing. And the second thing is also your starting solution should have lot of organization of the chains. The chains should have as much organization as possible in the starting solution, so that ultimately it helps in the final organization of the fibers. Ultimately you will get the fibers. So, if already in your solution it is organized, and then when you are forcing through the spinneret, there is little bit more organization that is happening. So, this actually is augmenting the final system. That means, in the final fibers that you are getting, you will have a lot of orientation of these chains along the length of the fibers, and that will give it the tensile strength that you want. So, in order to do that, you have to start with a highly concentrated solution in which there is a lot of organization, or a, let us say, this is not a very right term here, let us say high degree of organization of polymer chains is required in your starting solution for the processing. Okay. Now, something that you need to keep in mind here is the following. We are talking about rigid chains here. Normally polymers are flexible chains. So, when you dissolve in a solvent, they will have this kind of random, they will be like random coils, flexible chains. So, you may have this kind of random coils when you dissolve them in a solvent. In our case, we are talking about para-aramid molecules which are like random rods. Then when you dissolve them in a particular solvent, they will be like, they are rigid rods. So, this is a random rod configuration. When you increase the concentration, so this is in dilute solution, you dissolve in the solvent. I am not yet talking about what solvent we are using. Let us say we have the right kind of solvent that we want to use. So, at a low concentration you will have all these random rods that are there. When you increase the concentration, what will happen? There will be regional organization like this. So, in different regions you will have the chains organized like this. So, you will have this kind of domains of organized chains. This is what you have, this is what you call as a liquid crystalline state. So, the material is still liquid, but it is starting to have this kind of organization in the material. So, it will have a liquid crystalline state. So, obviously in all kinds of solvents, the same polymer when you dissolve, it will not form this kind of state. So, it depends on which solvent you are using. So, that you have to standardize first. So, you have gone to higher concentration. This situation is not existing here because we are talking about para-aramid fibers which are rigid rods. In para direction, in the para position you have all the functionalities of the aromatic rings, and this is also rigid because you have lot of aromatic units. So, that also provides lot of stiffness to the material. As I already told before, the aromatic units provide rigidity. So, liquid crystalline state. If you increase the concentration further, then what you will have is this kind of system. You will have a long range order throughout the material. So, all these chains are oriented along a certain direction. However, if you look at the center of these chains, the center of these chains are arranged randomly. So, all the chains are oriented along a certain direction, but if you look at all the centers, just take the centers of all these rods. If you just see this particular diagram, how are these centers arranged? These centers are arranged randomly. So, this particular situation where you have a long range order, but the centers are arranged randomly, this is going to give you a state which is called nematic phase, nematic liquid crystalline phase. This is the phase that you are looking for. If you start with this kind of phase, that means a solution of the polymer where the polymer is at least oriented like this. So, you now already have a lot of organization, a very high degree of organization of polymer chains in the solution, and after this through spinning process, which I am going to describe afterwards, you further align these materials. So, it helps if it is already aligned, that is the point, and then you will ultimately remove the solvent and you will get your fiber, that is the idea. So, it turns out that for this Kevlar or para-aramid, you have to use 100% H2SO4 sulfuric acid, and if you dissolved in 100% H2SO4 around 20% of this material, then what you will get is this nematic phase. Of course, you have to standardize this, because in all solvents this kind of phase may not generate. So, once you get this particular phase, what you do is that you pass it through a spinneret. So, if you now see the corresponding diagram in the PowerPoint slide. So, you will see that, for example, so this is your spinneret, this has all these holes in it, this exactly looks like your shower head in the bathroom. So, you are putting your polymer solution, which is highly concentrated solution in sulfuric acid 20% solution, and it is basically a nematic liquid crystalline phase. It has all these orientations of these chains, so on and so forth, blah blah, and then what you are doing, you push through these spinnerets and the polymer comes out through these little holes, and so you start to get the fibers already, and there is air in between, and then what you do is that you are passing this particular system through the water. So, this is water here. So, the fibers already, the filaments, let us say the filaments, they have already started to generate, and when you are having this coagulation bath here, it can actually remove the sulfuric acid that was there in the system. So, and then you are getting all these fibers, and you are using these guides that will guide them out of the coagulating liquid, and then you have a rotating bobbin on which you can have the as spun urn. I mean, you can spin this material like this, and you can have these rolls of these fibers, so on and so forth. So, this is a process which is called dry jet wet spinning. Wet spinning I have already mentioned the name, I did not mention, I mean, as far as the concept is concerned, I have not still gotten into the details of that, but this is the overall process. So, you do what you call as dry jet wet spinning, and you have a coagulating liquid. In this case, typically you can use water, and in fact the fiber here, it starts to solidify already in between when you have the air. So, it was sulfuric acid solution and it is coming here and in between. So, basically what you are doing is this solution that you are starting with, you are keeping it at a very high temperature. In this case, it is at 100 degrees Celsius. So, it is just coming out here, it is getting cooled down. So, it starts to solidify, the filaments start to appear, and then you are pushing the filaments through the water, and the water can take away the sulfuric acid that was stuck to the filaments, and then you take it out, so on and so forth. So, this is your dry jet wet spinning process. Now, let us come back to our script here. So, we will try to explain this particular situation a little further. Now, we were talking about spinning process. We were talking about spinning process, and we already talked about what you call as dry jet wet spinning. We showed you the schematic. The schematic is actually taken from the book of Chawla. I will attach that as the, of course, when I send you the study materials. So, dry jet wet spinning process, this is what you use for Kevlar fiber preparation, which prompts me to come to talking about in general what is a spinning process. So, what we will do is, because we are running out of time today, we will stop here and we will start right in the next class with the concept of fiber spinning process. So, until then, thank you and see you in the next class.